Have you ever wondered what sparked the grand spectacle we call the universe into existence? This question, as old as human curiosity itself, has captivated our collective imagination for eons. From the earliest cave-dwelling philosophers gazing up at the night sky to the most brilliant minds of the 21st century, humans have sought to understand the genesis of our cosmos. The universe's creation, its birth, if you will, is a concept that is as complex as it is profound. It's an enigma that has spawned countless theories, each more intriguing than the last. Theories that span from divine intervention to cosmic collisions and beyond. Yet, despite the vast sea of ideas, there is one theory that has, for now, withstood the test of time and scrutiny. It's a theory that takes us back nearly 14 billion years to a moment when all matter, energy, space, and even time itself was infinitely condensed. Our best guess to date is a fascinating theory known as the Big Bang. What existed before the Big Bang? An intriguing question, isn't it? But as we delve into this riddle, we find ourselves grappling with the very fabric of time and space. When we think of the term before, we naturally presume a preceding moment in time. Yet, the Big Bang isn't simply an event in time, but it's the very birth of time itself. It's the point where all our conventional understanding of chronology breaks down, and the idea of before starts to lose its meaning. So, if time began with the Big Bang, what does that mean for the concept of before? Well, some physicists propose that the concept of before becomes somewhat meaningless in this context. We're trying to apply our human understanding of time to a realm where it might not even exist as we know it. It's like trying to look north from the North Pole. There's simply no before to the beginning of time. Now, let's delve a little deeper. Consider the Big Bang not as an explosion in space, but as an explosion of space. Space, time, matter, and energy all sprung forth from a singular point of unimaginable heat and infinite density. This is what we refer to as the singularity. The singularity is a concept that defies our everyday intuition. It's a state of the universe where all matter is compressed to a single point, a point so dense and so hot that our current understanding of physics just can't describe what's happening. In this domain of extremes, the laws of quantum mechanics and general relativity, the two pillars of modern physics, come into conflict. The rules that govern atoms and particles break down. The principles that steer stars and galaxies cease to apply. In this singularity, the laws of physics as we know them cease to function. It's a place where our scientific understanding hits a wall. But it's also a place that may hold the secrets to the birth of our universe. It's a fascinating paradox, isn't it? The beginning of everything we know, a place where our knowledge ends. But the quest for understanding never ceases. And that's what makes this journey so incredibly exciting. So, how did everything evolve from this singularity into the universe we observe today? This, my friends, is the story of the Big Bang. Imagine the universe compressed into a state of infinite density, a singularity. Then, in less than a blink of an eye, an explosive expansion. This wasn't an explosion of matter into space, rather it was an expansion of space itself. This rapid inflation, faster than the speed of light, stretched the universe from a point of singularity into an enormous expanse. In these earliest moments, the universe was incredibly hot and dense. As it expanded, it cooled. After a fraction of a second, the basic particles of matter began to form. These were quarks and leptons, the smallest units of matter that we know of today. They were created out of pure energy as the universe cooled down. Now, these particles didn't immediately combine to form the atoms we're familiar with. The universe was still too hot for that. Instead, they existed in a state of plasma, like a cosmic soup. It wasn't until about 3 minutes after the Big Bang, when the universe had cooled down significantly, that these particles could combine to form the first atoms, primarily hydrogen and helium. With the formation of these atoms, the universe became transparent to light for the first time. The cosmic microwave background radiation we observe today is the afterglow of this moment, the first light of the universe. As the universe continued to expand and cool, matter began to clump together under the influence of gravity. These clumps grew denser and hotter, eventually igniting to form the first stars. These stars grouped together to form galaxies, and so the universe as we know it began to take shape. From a singularity of infinite density, the universe expanded and evolved into the vast, diverse cosmos we are part of today. It's a journey of cosmic proportions, from a point of unimaginable density to an expansive universe of galaxies, stars, and planets. And the journey continues, as our universe is still expanding, still evolving, still creating. The Big Bang Theory, while widely accepted, is often misunderstood and faces several challenges. Let's delve into some of the common misconceptions surrounding this remarkable theory. Firstly, the term Big Bang might suggest a colossal explosion. But here's the twist. It wasn't an explosion in the conventional sense. Instead, it was an expansion of space itself, with all the matter and energy of the universe contained within it. So, rather than picturing a dramatic burst of matter into empty space, imagine space itself expanding from a singular point, carrying matter and energy along with it. Now, let's address some of the challenges to the Big Bang Theory. The first one is the flatness problem. The universe, in broad strokes, appears to be flat rather than curved, which is puzzling considering the high precision required in the initial conditions of the universe to achieve this state. Next, we have the horizon problem. This conundrum arises from the fact that regions of the universe which are too far apart to have ever been in contact share the same physical properties. How could these regions be so remarkably similar without ever having interacted? Lastly, we come across the magnetic monopole problem. According to certain theories, the Big Bang should have produced a large number of magnetic monopoles, particles with just one magnetic pole. But here's the stumbling block. We've yet to detect a single one of these elusive entities. These challenges have spurred scientists to devise new theories and models, such as cosmic inflation, to address these issues. The beauty of science is that it continually evolves, adapts, and refines its understanding in the face of new evidence and fresh perspectives. But let's not lose sight of the bigger picture here. Despite these challenges, the Big Bang Theory remains our best explanation for the universe's origins. It continues to be a beacon of insight, guiding us in our quest to comprehend the enigma of our existence. Yet the Big Bang Theory leaves some questions unanswered. Indeed, despite its comprehensive explanation of the universe's infancy and subsequent expansion, there are mysteries that the Big Bang Theory does not elucidate. One of the most profound among these is the question of what initiated the Big Bang itself. What sparked this cosmic explosion? Was it a quantum fluctuation, a divine intervention, or something else entirely? We simply don't know. The Big Bang Theory also doesn't offer a satisfying answer to the question of what lies beyond our universe. Is our universe just one of countless others in a broader multiverse? Or is it unique, the lone cosmos in an infinite void? These are questions of such magnitude that they boggle the mind and challenge our understanding of reality. Then there's the future of our universe. The Big Bang Theory provides a genesis story, but it doesn't give us a clear picture of our universe's destiny. Will it keep expanding indefinitely, growing colder and emptier over time? Or will it eventually collapse in a cataclysmic big crunch? Or perhaps there's another fate awaiting us, something we haven't even conceived of yet. We're left pondering these questions, and many others, in the face of a theory that provides a framework, but not a complete picture. It's like having a jigsaw puzzle with many of the pieces missing. We can see the general image, but the details, the fine nuances, remain elusive. But this is not a cause for despair. Rather, it's a testament to the wonder of scientific inquiry. The unanswered questions are not dead ends. They are signposts, directing us toward the next phase of exploration and discovery. They remind us that our knowledge, while extensive, is not yet complete. They spur us on, fueling our curiosity and our thirst for understanding. As we continue to explore the cosmos, we may eventually find answers to these questions, furthering our understanding of this incredible universe we call home. The quest to understand our universe's beginnings is far from over. It's a pursuit that carries profound significance, not just for us as individuals, but for humanity as a whole. Every step we take in unraveling the mysteries of the cosmos brings us closer to understanding our place within it. Our thirst for knowledge is a testament to our innate curiosity, a trait that has propelled us from the confines of our planet to the vast expanse of space. We have come a long way, from gazing upon the stars with naked eyes to piercing through the cosmic veil with advanced telescopes and spacecraft. The importance of scientific exploration and discovery cannot be overstated. It's a beacon that guides us, illuminates our path, and fuels our journey toward understanding the unknown. Each new discovery is a piece of the puzzle, bringing us closer to the ultimate truth. As we gaze upon the stars, we are not just spectators, but active participants in this grand cosmic journey.